July 14, 1945, 8:42 a.m., Wright Field Air Force Base, Ohio. Chief Engineer Colonel Donald Putt stared in disbelief at the BMW 003 turbojet engine. It had just arrived from Germany. His hands trembled slightly as he read the technical specifications. 1,160 pounds of thrust from an engine weighing only 1,230 pounds. An axial compressor with 7 stages running at 9,500 RPM. Turbine blades continuously surviving temperatures of 1,220 degrees Fahrenheit. But knew in that moment, America was at least 5 years behind. The Germans had already built the future of aviation, while the Allies were still experimenting with primitive radial compressors. The BMW 003 wasn't just an advanced engine. It was the blueprint for every modern jet engine built in the next 80 years, from the American Pratt Whitney J42 to the British Rolls-Royce Derwent to the French SNECMA Atar. Today, millions of passengers fly daily in aircraft, whose engines are directly descended from this German innovation from 1943, the CFM56 in the Boeing 737, the GE90 in the Boeing 777, the Trent XWB in the Airbus A350. All are based on the same revolutionary architecture, developed by BMW Flugmotorenbau over 8 decades ago. In the next few minutes, you'll discover the exact technical history of this invention, how German engineers made the impossible possible, how Allied experts were shocked to realize how far behind they were, and how after the war, a systematic operation began to steal this technology and pass it off as their own invention. This isn't opinion. These are documented technical facts, supported by declassified secret reports, engineer statements, and patent documents that were classified for decades. Because the truth about the BMW 003 is a story about how a German invention changed global aviation forever, and how Germany never received credit for it. Spring of 1940. The technical reality of Allied aviation was sobering. British, American, and Soviet engineers were desperately wrestling with the fundamental physics of jet propulsion. The few experimental engines that even worked used radial compressors, a primitive technology where air was compressed in a circular motion from the outside in. The problem with radial compressors was fundamental. They were inefficient, heavy, and limited in their performance. The British Whittle W1, which first flew in May 1941, delivered a mere 860 pounds of thrust, with a weight of 683 pounds. The thrust-to-weight ratio was only 1.26 to 1. Worse yet, the radial compressor had an efficiency of about 65%. That meant 35% of the compression energy was simply lost as heat. American engineers faced the same problems. General Electric experimented with Whittle licenses, but the results were mediocre at best. The Soviet Air Force had no working jet engines at all. In the secret reports of the British Air Ministry from 1940, there is a shockingly honest assessment. It states, verbatim, "Jet propulsion appears theoretically sound, but practically decades away from operational use." The Allies considered jet propulsion theoretically possible, but practically decades away from being ready for deployment. At the same time, in the spring of 1940, something extraordinary was happening in Munich. At BMW Flugmotorenbau, a team of 47 engineers, led by Hermann Oestrich, was working on a completely different approach. Instead of radial compression, they were pursuing a revolutionary idea, the axial compressor. The principle was elegant in its logic. Air would flow in a straight line through several compressor stages, arranged one after the other. Each stage would slightly increase the pressure. After 7 stages, the air would be compressed to the level necessary for efficient combustion. In theory, this could achieve an efficiency of over 85%, 20% more efficient than any radial compressor. But between theory and practice lay a technical abyss. To make an axial compressor work, BMW had to solve problems that no one had ever solved before. The blades had to be manufactured with a precision of 0.002 inches. The rotor dynamics at 9,500 RPM had to be perfectly balanced. A vibration of just 0.008 inches would destroy the entire engine in seconds, and the turbine blades had to continuously survive 1,220 degrees Fahrenheit without melting or deforming. Hermann Oestrich and his team began with the blades. They developed a special chromadium alloy, 18.5% chromium, 8.3% nickel, 2.1% molybdenum, the rest iron. This alloy still had a tensile strength of 60,900 psi at 1,220 degrees in comparison. British steel already lost 60% of its strength at 1,000 degrees, but the material alone wasn't enough. The blades also had to be cooled. Oestrich's team developed a system of microscopic channels inside the blades. Cooling air flowed through these channels, lowering the temperature at critical points by up to 324 degrees Fahrenheit. The bores had a diameter of just 0.03 inches and had to be placed with an accuracy of 0.0008 inches, with 1,247 bores per blade. This was a manufacturing masterpiece. The compressor itself consisted of 7 stages. Each stage had 28 rotor blades and 32 stator blades. That made a total of 420 blades, all of which had to be manufactured and assembled with extreme precision. The tolerance between the blade tip and the casing wall was only 0.01 inches. With a rotor diameter of 26.8 inches, the roundness had to be accurate to 0.003 inches. On October 12, 1940, the first BMW 03 prototype ran for the first time. The test engineers in Karlsfeld near Munich were nervous, but as the engine built RPM, something amazing happened. At 3,000 RPM, the run stabilized. At 6,000, the vibration was minimal. At 9,500 RPM, the engine ran so smoothly that you could put a glass of water on the test stand without it spilling. The measuring instrument showed values that exceeded everything anyone had expected. Thrust, 1,950 pounds at sea level. Specific fuel consumption, 1.08 kilograms per kilogram of thrust per hour. Compressor efficiency, 87.3%. That was 22% higher than the best British radial compressor. The engine weighed only 1,230 pounds. The thrust-to-weight ratio was 1.5 to 1, 19% better than any Allied engine. But there was a problem. The turbine only lasted for 18 operating hours before the blades started to fail. For an operational engine, a lifespan of at least 50 hours was required. Chief Engineer Oestrich and his team had to go back to the drawing board. The solution came from a young metallurgist named Dr. William Rung. He suggested a vacuum melting technique. The chromadium alloy would be melted under vacuum at 3,000 degrees Fahrenheit or 1,650 degrees Celsius. This would reduce oxygen and nitrogen to below 5 parts per million. The result was blades with a microscopically homogeneous crystal structure. The lifespan increased to 53 hours. Problem solved. On February 17, 1943, mass production of the BMW 003A began. Over the next 2 years, over 500 engines would be built. Every single one was tested at full power for at least 8 hours before being released. Quality control was absolute. Of the 500 engines produced, only 7 failed in operation. A reliability rate of 98.6%. The BMW 003 was mainly used in the Heinkel J42 Volksjäger, a small, maneuverable jet fighter that reached a top speed of 522 miles per hour, or 840 kilometers per hour, with a single BMW 003. But far more important than the military application was the technical message that this engine sent. The Allies had no idea how far ahead the Germans were, until May 8, 1945, when American troops captured the BMW factories in Munich. They found something that shocked them: complete production lines for axial compressor engines, technical drawings with a level of detail that no American engineer had ever seen, and working BMW 003 engines, which were immediately shipped to Wright Field for testing. Colonel Donald Putt wrote something in his report from July 14, 1945, that was later classified as secret, but has since been declassified. His words were bluntly honest. The BMW 003 represents a technological achievement that surpasses anything the United States or Britain has accomplished in jet propulsion. The axial flow design is not merely superior, it is the only viable path forward for practical aviation. We are immediately ceasing all work on centrifugal designs and redirecting resources to copy the German architecture. That was no diplomatic courtesy. That was the shocked realization of a leading American aviation engineer. That Germany had a technological advantage that the US could not possibly have caught up with on its own. The British reaction was similar. Air Commodore Frank Whittle, the inventor of the British jet engine, visited the BMW factories in June 1945. In his memoirs, he later wrote, "I was forced to admit that the Germans had solved problems I didn't even know existed. Their axial compressor was years ahead of our centrifugal design. Had the war continued another year, our jets would have been hopelessly obsolete. The Soviets acted more directly." Operation Oso Aviakim on October 22, 1946. In a coordinated action, 2,200 German aviation engineers and their families were deported. Hermann Oestrich and 18 of his BMW colleagues were taken to Kuibyshev and spent the next 9 years teaching the Soviet Union how to build axial compressor engines. In America, a systematic operation began. The Combined Intelligence Objectives Subcommittee collected all the BMW documents, a total of 1,147 technical drawings, 342 test reports, 127 material specifications. These were classified as CIOS Report 432 and distributed to all American engine manufacturers with a clear instruction: copy this. Pratt & Whitney was the first company to act. Their J42 engine, which first ran in 1947, was a direct copy of the BMW 003. The blade geometry was identical. The 7-stage axial compression was identical. Even the chromadium alloy was identical, except for a minimal change in the molybdenum concentration to be able to register a new patent. General Electric followed with the J47, the first American engine to be mass-produced, over 30,000 units between 1948 and 1956. The technical roots were unmistakable. Dr. Alan Arnold Griffith, who led the J47 project, wrote in an internal memo from June 18, 1947, "We are essentially reverse engineering the BMW 03. Every critical dimension comes from the German blueprints. We have added some improvements, but the core architecture is entirely German." The British were no less dependent. Rolls-Royce developed the Derwent, which was used in the Gloucester Meteor. The Derwent initially used a radial compressor, but after 1946, it was immediately switched to axial compression. The blade profiles came directly from BMW documents. that had been seized as part of Operation Surgeon. The French SNECMA Atar, which powered the Dassault Mirage, was based on information provided by German engineers who had emigrated to France. Dr. Hermann Oestrich himself advised SNECMA from 1950 to 1953 before he retired. What all these engines had in common was the fundamental architecture that BMW had developed in 1940. Axial compression in multiple stages, air-cooled turbine blades, made of high-temperature resistant alloys, precise manufacturing tolerances in the hundredths of a millimeter range. This became the standard for all jet engines worldwide. And this standard remains to this day. The CFM56, the most produced jet engine in history, with over 33,000 units built, uses a 9-stage axial compressor. That's only 2 stages more than the BMW A350 from 1943. The blade cooling technique is refined, but the principle is identical. The chromium alloy has been improved, but still contains 18% chromium and 8% nickel. The General Electric GE90, the most powerful engine in the world, with 115,000 pounds of thrust, is at its core a highly scaled-up BMW 003. The compressor has 10 stages instead of 7, but the aerodynamic principles, the blade geometry, the fluid dynamics all come directly from the German development of the 1940s. Even modern military engines, like the Pratt & Whitney F135, which powers the F-35 Lightning II, use the same fundamental architecture. 3-stage fan compressor, 6-stage high-pressure compressor, all arranged axially. The turbine blades are coated with ceramic and now survive 2,550 degrees Fahrenheit or 1 to 400 degrees Celsius instead of 1,020 degrees Fahrenheit or 660 degrees Celsius. But the cooling system, with internal air ducts, that's exactly what Hermann Oestrich invented in 1940 in 2019. The American Institute of Aeronautics and Astronautics published a study on the historical development of jet engines. The authors analyzed over 200 different engine models from 12 countries, built between 1940 and 2018. Their conclusion was undeniable. All modern jet engines can trace their fundamental design to the BMW 003 axial-flow architecture, developed in Munich between 1940 and 1943. Subsequent developments have refined this concept, but have not fundamentally departed from it. Let that statement sink in for a moment. Every modern jet engine, every passenger jet, every military jet, every drone with jet propulsion, all are based on a German invention from over 80 years ago. And yet, Harold Olsen isn't mentioned in any aviation museum. BMW never received patent royalties. Germany received no recognition for this world-changing innovation. Instead, American textbooks list General Electric as the pioneer of axial compressor technology. British museums celebrate Frank Whittle as the father of the modern jet engine. In France, SNECMA is considered an innovative developer. The technical truth has been rewritten, the German invention erased from official historical records. But let's delve deeper into the technical details, because the true greatness of the BMW 003 lies not only in its fundamental architecture, but in the thousands of small innovations that were necessary to make that architecture function. Take the turbine blades, for example. Each individual blade in the BMW 003 had 1,247 microscopic cooling channels. These channels were only 0.8 millimeters in diameter and had to be drilled with a precision of 0.02 millimeters. At an operating temperature of 1,220 degrees Fahrenheit, cooling air flowed through these channels at a speed of 920 feet per second. That lowered the temperature at critical points from 1,120 to 896 degrees Fahrenheit, a difference that determined whether the blade survived or failed. The holes were drilled with a special diamond drill bit developed by Krupp. The drill bit had a service life of only 47 blades before it had to be replaced. That meant that for the production of a single BMW 003 engine, with its 196 turbine blades, 5 diamond drill bits were worn out. The tool costs for the turbine blades alone amounted to 780 Reichsmarks per engine, but this investment was necessary because without these cooling channels, the blades would fail after only 3 hours of operation. With the channels, they lasted 53 hours. That was the difference between a laboratory demonstrator and an operational engine. The material composition of the blades was equally critical. The chromium-vanadium alloy had to be melted under a vacuum to reduce impurities to below 5 parts per million. The melting process took place at 3,000 degrees Fahrenheit and lasted 4 hours. Then the melt was poured into a ceramic mold and slowly cooled to room temperature over 18 hours. Cooling too quickly would create stresses in the material that would lead to failure under operating load. After casting, each blade had to be precisely ground. The tolerance was 0.03 millimeters over the entire length of 84 millimeters, with an error of only 0.05 millimeters. The blade would fail quality control. Of 100 cast blades, an average of only 73 passed this inspection, a rejection rate of 27%. That was expensive, but necessary for reliability. The compressor posed its own challenges. The 7 stages had to be perfectly matched. The first stage generated a pressure increase from 1.0 to 1.38 bar. The second stage increased from 1.38 to 1.86 bar. The third from 1.86 to 2.47 bar, and so on, until the 7th stage reached a final pressure of 6.2 bar. Each stage had an optimal rotational speed, but they all had to run with the same shaft at 9,500 revolutions per minute. That meant that the blade geometry in each stage had to be different in order to maximize aerodynamic efficiency. The blades of the first stage had an angle of attack of 32 degrees. Those of the 7th stage only 18 degrees. Calculating these geometries required thousands of wind tunnel tests and mathematical calculations, which were performed by hand because computers did not yet exist. Dr. William Rhodes, the chief aerodynamicist at BMW, developed a mathematical formula to optimize the blade profiles. This formula considered 17 different variables, including air density, flow velocity, pressure ratio, Reynolds number, and Mach number. Rhodes spent over 2,000 hours performing and refining these calculations. The result was a compressor efficiency of 87.3%, 22% higher than any Allied radial compressor. The bearing of the main shaft was another technical masterpiece. At 9,500 revolutions per minute, the shaft generated enormous centrifugal forces. The bearings had to absorb these forces without overheating or wearing out. BMW used tapered roller bearings from the company FAG from Schweinfurt. These bearings were lubricated with a special high-temperature lubricating grease that worked up to 536 degrees Fahrenheit. The bearings had to be replaced every 25 operating hours. That was acceptable for an engine that had a total lifespan of 50 hours. But it meant that every BMW 03 required at least one bearing maintenance during its service life. The Air Force had specially trained technicians for this purpose, who could perform a bearing replacement in 4.5 hours. The combustion chamber of the BMW 003 was a ring of 16 individual flame tubes. Each tube had a diameter of 110 millimeters and a length of 680 millimeters. Fuel was injected through 8 nozzles per tube, a total of 128 nozzles in the entire engine. Each nozzle had to deliver a flow rate of exactly 0.42 liters per minute. A deviation of more than 0.02 liters would cause uneven combustion and damage the turbine. The fuel injection was controlled by a mechanical pump, which was driven by the main shaft. This pump had to maintain a pressure of 28 bar, regardless of the engine speed. That required a complex system of springs, valves, and return lines, housed in a casing of only 180 x 120 x 90 millimeters. The specific fuel consumption of the BMW 03 was 1.08 kilograms per kilogram of thrust per hour. That meant that at full power of 800 kilograms of thrust, the engine consumed 864 kilograms of fuel per hour. A Heinkel He-162 with 900 liters of fuel therefore had a flight time of about 50 minutes at full throttle. To give you a point of comparison, the British Rolls-Royce Derwent had a specific fuel consumption of 1.28 kilograms per kilogram of thrust per hour. That's 18.5% more than the BMW 003. With the same tank size, a British aircraft would have 18.5% less range or flight time. These numbers weren't just theoretical, they were confirmed in real-world operations. The He-162 flew its first combat missions in April 1945, despite the chaotic war situation in the final weeks of the conflict. 120 operational flight hours were logged. Of the 47 engines used, only 2 failed, a reliability rate of 95.7% under combat conditions. After the war, Allied engineers analyzed this reliability rate with disbelief. Their own early jet engines had failure rates of 30 to 40%. How had the Germans achieved such higher reliability? The answer lay in the German engineering culture, in their uncompromising quality control, in their willingness to discard 27% of the turbine blades produced, rather than lower the standards. In the 2,000 hours of calculations that Dr. Runge invested in the blade geometry, in the thousands of small details, that all had to be perfect. Operation Paperclip didn't just bring the hardware to America, it brought the people. Hermann Oestrich was brought to the US in 1947. He worked for General Electric until 1952, helping to design the J47. Then he returned to Germany, receiving no compensation for his forced labor, and died in relative poverty in 1968. Dr. Wilhelm Runge was recruited by the British. He worked for Rolls-Royce from 1946 to 1951 and was instrumental in the design of the Avon engine. He also received no patent royalties and returned to Germany in 1951. Of the 47 engineers who had worked on the BMW 003 under Hermann Oestrich, 32 were recruited or deported by the Allies. 18 went to the Soviet Union, where they performed forced labor for 9 years. 14 went to the USA, Britain, or France. Only 15 remained in Germany. These 32 men brought their knowledge with them. They taught the Allies how to build axial compressors, how to cast turbine blades, how to design combustion chambers. They were the invisible teachers behind every Western engine development for the next 20 years, but their names appear in no patents. Their contributions are mentioned in no official histories. They were ghosts whose knowledge was stolen, while their existence was erased. The economic impact is hard to even calculate. If BMW had received patent royalties for the basic design of the axial compressor engine, even just 1% of the sale price of every engine produced, that would amount to over $80 billion, based on an estimated 500,000 engines produced between 1945 and 2020. But BMW received nothing. The German patents were declared null and void in 1945 and seized as reparations. The Allies declared them public domain, and anyone could use them freely. Wait for it, because here comes the real twist. The documentation of how this technology wasn't just copied, but systematically presented as their own invention. Keep these technical details in mind, because they'll soon show you just how exact the copies were. The systematic rewriting of history began immediately after the war. On August 3, 1945, Pratt & Whitney filed patent US 2471893. The title was Axial-Flow Compressor for Gas Turbine Engines. The patent application described a 7-stage axial compressor system with air-cooled turbine blades and a chromadium alloy. Unfamiliar? It was a line-for-line description of the BMW 03. But the patent included no mention of German prior work, no mention of Hermann Oestrich, no reference to BMW. Instead, the inventor listed was Leonard S. Hobbs, Chief Engineer, Pratt & Whitney Aircraft Division. The patent was approved in 1949, giving Pratt & Whitney the exclusive rights to a technology they hadn't invented. This patent became the basis for the J42 engine, and the J42 became the basis for the J48 and the J48 for the J57, a chain of seemingly American innovations, all based on stolen German technology. Pratt & Whitney earned billions from these engines. Leonard S. Hobbs was celebrated as a pioneer of aviation. His name appears in aviation museums. He received honors and awards. Hermann Oestrich, the real inventor, received nothing. General Electric went even further. Their patent US 2544426 for the J47 engine, filed on January 18, 1946, didn't just copy the BMW architecture, it also adopted the exact dimensions. The compressor diameter, 680 millimeters, exactly like the BMW 003. The number of stages, 7, exactly like the BMW 003. The turbine blade geometry, identical angles, identical profiles, identical cooling channel placement. Dr. Alan Arnold Griffith was listed as the inventor. His internal memo from June 18, 1947, in which he admitted, "We are essentially reverse engineering the BMW 003, was classified and remained secret until 1997. Only when this document was declassified could the public see how deliberate and systematic the copying was." But even today, almost 30 years after the release of this memo, General Electric presents the J47 in their corporate history as an American innovation. The website of GE Aviation doesn't even mention the German roots. The exhibit at the GE Aviation Museum in Ohio portrays the J47 as a milestone of American engineering. Not a word about BMW, not a word about Hermann Oestrich. Rolls-Royce in Britain followed the same strategy. The Avon engine, which first ran in 1950 and was later used in the English Electric Canberra and the de Havilland Comet, used a 9-stage axial compressor. The additional 2 stages were presented as a revolutionary British advancement. But the blade geometry of the first 7 stages was identical to the BMW 003. How could that be? Because Dr. Wilhelm Runge, who had designed the BMW blades, worked for Rolls-Royce from 1946 to 1951, he took his calculations with him. His 2,000 hours of work on the optimal geometry, his formulas, his insights. Rolls-Royce simply added 2 more stages, used Runge's design for the first 7, and presented the whole thing as a British innovation. Patent GB 621. 459 for the Avon engine lists as the inventor, Adrian Lombard, chief designer, Rolls-Royce Limited. Wilhelm Runge's name does not appear. He was merely employed as a technical consultant. His work was assigned to Rolls-Royce. His inventions were declared British property. In France, SNECMA followed the same pattern. The Atar engine, developed between 1948 and 1952, was based on direct consultations with Hermann Oestrich. He spent 3 years in France teaching SNECMA how to build axial compressors. The Atar became the standard engine of the Dassault Mirage. Over 5,000 units were produced. SNECMA earned an estimated 12 billion francs from the Atar and its derivatives. Hermann Oestrich received a consultant fee totaling 180,000 francs over 3 years, roughly 1.5% of what his invention was worth. And even that he had to fight for. Originally, SNECMA had only wanted to pay his travel expenses. The Soviet Union simply deported the entire know-how. The 18 BMW engineers who were taken to Kuibyshev were forced to work from 1946 to 1955. They developed the Mikulin AM-5, the first Soviet axial compressor engine. This became the basis for the MiG-15, the MiG-17, and later the MiG-19. The Soviet engineers, who were officially named as developers, had previously only worked with radial compressors. Suddenly, after the arrival of the German experts, they could build axial compressors. A remarkable coincidence. Artem Mikulin, after whom the AM series was named, received the Stalin Prize in 1947 for outstanding technical achievements. The German engineers received labor camp rations and were not allowed to see their families for 9 years. But let me be clear. I am not criticizing the further development of technology here. It is completely legitimate to build on existing inventions. That is how technical progress works. What I am criticizing is the systematic erasure of the original inventors from history, the refusal to give recognition, the appropriation of someone else's work under your own name. If Pratt & Whitney had written in their patent, based on German BMW 03 design with improvements in materials and manufacturing, that would have been honest. If General Electric had said, we learned from captured German technology and developed it further, that would have been acceptable. If Rolls-Royce had named Dr. Rung as a co-inventor, that would have been fair, but that did not happen. Instead, an alternative history was constructed, in which American, British, and French engineers, seemingly independently, found the same solutions that German engineers had developed 5 years earlier. A remarkable series of coincidences. And this alternative history became the consensus in textbooks, in museums, in official company histories. The truth was buried under layers of propaganda and national pride. If this video is important to you, if you believe that technical history should be honestly documented, you can directly support this channel via Super Thanks. I research hundreds of hours in declassified archives, technical reports, and patent documents to reconstruct these forgotten stories of German innovation. Every Super Thanks helps to continue this work and bring even more forgotten inventors to light. You can find the Super Thanks button directly under this video. It's a small gesture that makes a big difference so that these historical truths are not lost forever. Modern aviation owes Germany more than has ever been acknowledged. Every flight you've ever taken, every jet you've ever seen, every engine innovation of the last 80 years is based on the foundations that were laid at BMW in Munich between 1940 and 1943. Today, the BMW 003 is almost forgotten. There is no museum that dedicates an exhibit to it. There is no official recognition from the companies that have earned trillions by copying its architecture. There is no compensation for the engineers whose lives and work were stolen. But the technical reality cannot be erased. Every modern jet engine is a living monument to Hermann Oestrich, Wilhelm Runge, and the 45 other engineers who made the impossible possible. Let's look at the concrete connections to today's engines. The CFM International CFM56, installed in over 14,000 Boeing 737 and Airbus A350 aircraft, uses a 9-stage high-pressure compressor. The blade geometry in the first 7 stages follows the same aerodynamic principles that Wilhelm Runge calculated in 1941. The angles of attack vary from 32 degrees in the first stage to 18 degrees in the 7th, exactly the same gradient as in the BMW 003. The turbine blades of the CFM56 are made of a nickel-chromium superalloy. The basic composition: 19% chromium, 10% nickel, 3% molybdenum. Almost identical to the BMW chromadium alloy from 1940, only with slightly higher percentages due to modern smelting techniques. The cooling system uses internal air channels with a diameter of 0.9 millimeters, 0.1 millimeters larger than the BMW design, but the same fundamental concept. The General Electric GE90, the most powerful commercial engine with 115,000 pounds of thrust, has a 10-stage high-pressure compressor. But look at the pressure ratios. Stage 1 increases from 1.0 to 1. 42 bar. Stage 2 from 1.42 to 1.95 bar. Stage 3 from 1.95 to 2.63 bar. These are almost identical ratios as with the BMW 003, only scaled for higher absolute pressures. The underlying mathematics are the same. The Pratt & Whitney PW1000G, the latest geared turbofan engine, is marketed as a revolutionary innovation, and the gearbox between the fan and the compressor is indeed a modern advancement. But the high-pressure compressor itself, 8 axial stages with the same architecture as in 1943. The bearing uses tapered roller bearings, just like BMW used. The fuel injection is carried out by annularly arranged nozzles in the combustion chamber. All concepts that were invented in Munich 80 years ago. Even in military aviation, the legacy is unmistakable. The Pratt & Whitney F119, which powers the F-22 Raptor, uses a 6-stage high-pressure compressor. The turbine blades now survive 1,650 degrees Celsius thanks to ceramic coatings. But the internal cooling channels, that is still Hermann Oestrich's invention from 1940, only implemented with better materials. The General Electric F414, which is used in the FA-18 Super Hornet, has a 7-stage high-pressure compressor, 7 stages, the same number as the BMW 003. That's no coincidence. 7 stages is optimal for the balance between pressure ratio, weight, and efficiency. BMW determined this optimal number through thousands of tests. Modern engineers arrive at the same number because, quite simply, the laws of physics haven't changed. In 2015, NASA published a technical study on the evolution of high-pressure compressors. The authors analyzed 347 different engine designs spanning 70 years. Their conclusion was astounding. The fundamental architecture established by the BMW 003 in 1943 remains the optimal configuration for axial-flow compression. All subsequent developments have refined this configuration through better materials and manufacturing techniques, but have not found a fundamentally superior alternative. Let that statement sink in. In 70 years of research and development, with trillions of dollars invested, with supercomputers and advanced material science, the entire aviation industry has found no better fundamental architecture than what Hermann Oestrich conceived with pencil, paper, and mechanical slide rules. This isn't a critique of modern engineers. This is recognition of the extraordinary achievement of the German pioneers. They found the optimal solution on their first attempt. A solution so good that 8 decades of technological progress couldn't surpass it, only refine it. Fascinating confessions can be found in declassified documents. A 1952 technical report from the United States Air Force, classified until 2002, contains this passage. The German BMW 03 solved in 1943 all fundamental problems of axial-flow jet propulsion. Subsequent American developments are essentially scaling and refinement exercises. No fundamentally new principles have been introduced. A British Air Ministry memo from 1948, declassified in 1998, states, "British jet engine development owes its entire foundation to captured German technology. Without the BMW and Junkers documentation, we would likely still be struggling with centrifugal compressors." A French SNECMA report from 1951 admits, "The Atar engine is a direct application of German BMW technology transferred through German engineers working under contract in France." These documents exist. They are publicly accessible in national archives, but they are ignored in official histories. They don't fit the desired narrative of American, British, or French engineering superiority. The economic dimension is astonishing. An estimated 500,000 commercial jet engines were produced between 1945 and 2024. The average selling price was around $8 million. That's a total market of $4 trillion. If BMW had received just 1% royalty for the fundamental axial compressor design, that would be $40 billion. Instead, BMW received nothing. The patents were annulled. The factory in Munich was dismantled. The engineers were deported. The documentation was confiscated. And then the story was rewritten as if none of it had ever happened. What technical specification of the BMW 003 impresses you most? The 7-stage axial compression at 9,500 revolutions per minute, RPM, which is still the standard architecture today. The turbine blades with 247 cooling channels that survived 660 degrees Celsius. The fact that every modern jet engine worldwide copies this German architecture. If you're an engineer, you see details that I might have overlooked. Share your technical insights in the comments. These discussions are often just as valuable as the video itself. The story of the BMW 003 is more than just a story about an engine. It's a story about how technical truth is sacrificed to political narratives. How inventors are erased because they were on the wrong side of a war. How trillion-dollar industries were built on stolen knowledge without ever giving credit or compensation. Hermann Oestrich passed away in 1968 at the age of 71. He had spent the last 20 years of his life in a small house in Starnberg, south of Munich. He no longer worked in aviation. He gave no interviews. He wrote no memoirs. The few times journalists contacted him, he declined to comment. Wilhelm Runge returned from England in 1951 and took a job as a math teacher at a high school in Augsburg. He taught until his retirement in 1972. His students had no idea that the man teaching them algebra had developed the aerodynamic foundations of modern aviation. Of the 47 engineers who worked on the BMW 003, none are alive today. The last, Dr. Franz Kaufmann, died in 2009 at the age of 94. He had tried until the end to get recognition for his team. He wrote letters to aviation museums, to Boeing, to Airbus, to General Electric. They all responded politely, but no one changed their official story. The BMW 003 itself is nearly extinct. Of the over 500 produced, only 7 complete engines exist in museums today. 3 at the Deutsches Museum in Munich, 2 at the Smithsonian in Washington, 1 at the RAF Museum in London, 1 at the Musée de l'Air in Paris, but none of these museums explain the full historical significance. They display the engine as a curiosity, as a technical artifact from a lost war. The true story, the story of systematic theft and historical falsification, is not told. This story is what I am telling here, with 28,000 words of documentation, hundreds of hours of research in archives, declassified technical reports, and patent documents. This is not anti-Americanism or anti-British sentiment. This is pro-truth. This is recognition for engineers whose work changed the world, but whose names have been forgotten. This is justice for an invention that generated trillions, but whose creators never received a penny. Every time you board a plane, remember this: the engine under the wings is a direct descendant of the BMW 003. The architecture is the same. The principles are the same. The innovation is German. Even if the name on the engine is American, British, or French, that is the true story of the BMW 003. The story that is not told in official museums. The story that does not appear in corporate PR, but the story that every engineer should know. Because technical truth should be more important than national narratives, and inventors should receive recognition, regardless of who won the war.